Hi students, in this first video for chapter 9 and lecture 16, we are now going to talk about the chemical reactions that you are going to see in solution. The first reaction we will talk about is the precipitation reaction. This is such an important reaction is that it will get its own video part. A precipitant is an insoluble solid that separates from solution. So as we can see by this reaction here, we are going to take lead nitrate, mix it with sodium iodide, and we're going to end up with our lead iodide. This is going to be a solid and precipitate out of solution. Now, there are many terms that we can use for our precipitation. Precipitate, form a solid, crash out. There's a lot of different vernaculars that I want you to be familiar with. But notice that we are taking aqueous reactants, and after an ion switch of partners, one of our products is going to form a solid. This can be done using a molecular equation showing everything in our reaction going on and occurring. As you can see by the picture on the left, once we started to add the sodium iodide, notice that we are starting to form a yellow solid that is precipitating to the bottom of our test tube. The nice part about this is that we can go and turn this into an ionic equation. This means using a certain set of rules, the solubility rules, in which you'll learn later, you're going to find out which ions are going to split up in solution. We have done that here. But then notice that our lead iodide stays together because he is an insoluble compound. That is the importance of knowing those solubility rules. Then what we are able to do for our precipitation reaction is cancel out species that show up as identical parts and identical phases on both sides. So you can see here that we got rid of the nitrate and the sodium because this is going to be a spectator. This will lead us to what we call is our net ionic equation. This is telling us exactly what parts are going and forming our insoluble solid. Once again, you are going to see this reaction in great detail and be able to not only predict which species will precipitate, but also be able to calculate that using gravimetric analysis. Our second type is going to be the acid-base reaction. Acid-base reactions are important because they are a very common day occurrence, and you have seen them in great detail. So let's talk about acids first. Acids have a sour taste. Vinegar owes its taste to acetic acid, and we see a lot of citrus fruits that contain citric acid or phosphoric acid, and that's what gives it the tangy flavor. These also cause color changes in plant dyes. This is how you can see if there has been an acid spill near a farm, is that it will change the color of the chlorophyll of the neighboring plants. They react with certain metals to produce hydrogen gas. As you can see here, if I have HCl mixing with my magnesium solid, I will get magnesium chloride and hydrogen gas. Finally, they react with carbonates and bicarbonates to produce carbon dioxide gas. This is a very common reaction that you would see to neutralize the reaction, and that is why you will take baking soda and put it on an acid spill in order for it to leave. As you see here, here is my HCl mixing with our calcium carbonate. We get calcium chloride, which is a soluble salt, CO2, and water. This is a very nice way of getting rid of an acid. Aqueous solutions of acids love to conduct electricity. We will see what that means in a future video when we start talking about electrolytes and their uses. Finally, one of the reaction types that we're going to see today is a large group of family called the redox reactions. These are going to be reactions in which we transfer electrons. So you're going to have to be very careful to see where the electrons go and how the charges change of our reactants and our products. So in one part of our reaction here, you are seeing that 2 magnesiums go to 2 magnesium 2 plus and 4 electrons. This means that it is going to have lost electrons. This is what we call the oxidation half reaction. So the loss of electrons is known as the oxidation. Now we need something to pick up those electrons. So in this case, we will come along with oxygen, which is wanting electrons. It will pick up those 4 electrons and form 2 O2 minus. If they are going to gain electrons, we are going to call that the reduction half reaction. For every redox reaction, we are going to have a gainer and a loser of electrons. You must have one with the other in order to maintain charge balance. So now, as you can see here in our balanced chemical equation, we have 4 electrons on both sides. So that means we could cancel those out and we would be okay to go and have a balanced chemical equation and a balanced redox reaction. So we would end up with 2 Mg and O2 going to 2 MgO. It's really important that you are able to notice which species are gaining electrons and which ones are losing them. There is a bunch of subfamilies that come in our redox reactions. So the first one we want to talk about is very similar to the reaction that we just saw, and that is the combination reaction. The combination reaction is going to take 2 reactants and form 1 product. So as you see here, we are taking aluminum, adding it to our bromine, and getting aluminum bromide. Now, the reason that this works is that we have a state in redox called the oxidation number. This is going to help us give a count of the charge on the element at that time. For our elements, as you see here, we are going to have oxidation numbers of 0. We will be teaching you the oxidation numbers when we get to the redox video later in this chapter. But then when you go and form the ionic compound, notice that you are going to get a charged species. So based off of this, you can see that aluminum went from 0 to 3+. That is getting more positive. So that means that it is lost electrons. Where did those electrons go? Well, notice that our bromine going to bromide has gone from 0 to 1 minus. That is a gain of electrons. So if you see a species in which we get more positive, they will have lost electrons. If it becomes more negative, they will have gained those electrons. We can also do a decomposition reaction, which obviously is going to be the breakdown of a species. So as you see here, I have potassium chlorate, and if I do a reaction, I will get potassium, chloride, and molecular oxygen. How do we know that this is a redox reaction? Well, our potassium will have a 1+ charge, and it will have a 1+ charge over on the right side here in a moment. But then look at our chlorine that went from +5 and is now -1. This got more negative. So more negative means that it has gained electrons. So the important part here is that you will look at the oxygen, which went from 2- to 0. That is a loss of electrons. So in this case, we know that the reduction happened by gaining electrons for what you see in the chlorine, while the oxidation occurred for the oxygen. Probably the most well-known of the redox reaction is the combustion reaction. Now, many of you might not know who these two are, but this is Beavis and Butthead, and they were very famous for a TV show in the late 90s, early 2000s, and all they ever wanted to do was light stuff on fire. So in this case, we are going to take some atom, mix it with oxygen, and form a product. So now we are going to take sulfur plus oxygen and create sulfur dioxide. Most combustion reactions are going to be a hydrocarbon, carbon and hydrogen, and a mixture of oxygen going to form carbon dioxide. But I want you to see that a combustion reaction can happen with just more than carbon and hydrogen. So as you see here, the sulfur had the oxidation number of 0. So did my molecular oxygen. But now as I go to my product, our sulfur is +4, while oxygen is -2. This is a good combustion reaction. Another combustion reaction that you saw is the one that we started today's lecture with. Our magnesium mixing with oxygen goes and forms magnesium oxide. When we actually do this in a laboratory setting by igniting magnesium metal, you produce a brilliant, bright white flame. For this reaction, let's take a look at our oxidation numbers. Our magnesium will have been 0, Our oxygen will have been 0 because it is going to be in its elemental state. But if we go to the products, notice that magnesium goes to 2 plus. If it became more positive, that is the oxidation or loss of electrons. So let's find our reduction. Notice that that happens with our oxygen by going from 0 to 2 minus. Finally, we are going to talk about a couple of reactions that can be very difficult to see, but are very important for our chemistry. The first one is the displacement reaction. That is when we are going to remove a element or atom from a compound and replace it with another one. So let us go here and look at strontium plus water now gives us strontium hydroxide and hydrogen. Notice that we are displacing hydrogen in our water. So if we look at our water and we were to say that this is HOH, now our strontium is just taking the place of that hydrogen. So this is a hydrogen displacement. So our strontium was 0. It was +1 for our hydrogen. Then on the other side, you will notice that our strontium goes to +2 and our hydrogen goes to 0. This is a successful redox reaction. Now I can look at my titanium chloride plus magnesium. Notice that the titanium has been removed. This is what we call a metal displacement. In a metal displacement, we are going to exchange partners in the metal. So as you can see here with our titanium, will now be replaced with our magnesium, and we get free titanium in our product. So now let us go to our last group. And as you will see here, I have chlorine and potassium bromide going to form potassium chloride and bromine. This is what we call a halogen displacement. A lot of places will also call this a halogen exchange. And notice that we are just going and taking our chlorine, which had an oxidation number of 0. Our bromine was -1. So now our chlorine is -1. So to go from 0 to -1 is the reduction because it has gained electrons, while our bromine has been oxidized and has lost an electron. The final reaction we want to talk about is the disproportionation reaction. The disproportionation reaction can be very difficult to see, but once you see it, it is actually a very impressive reaction. This is where the same element is simultaneously oxidized and reduced. Now, most people will think that that means that the element and atoms are the same. This means that the same element type, but different atoms of that element are going to do the different processes. Now you'll see that our chlorine plus 2 hydroxides is going to give us ClO minus, Cl minus, and water. So we know that our chlorine is going to have a 0 oxidation number. So let's go ahead and take a look on the right side. The oxidation number in our ClO minus is actually +1, and we will talk about how to get that in our further video of oxidation numbers. And then you'll also see that chloride gets a -1. So we have the same element going and doing both processes. It was not the same atom of the element, but different atoms of the same element, and this is the disproportionation reaction. So now you can see that we have the oxidation and the reduction occurring by the same material. So let's try a couple examples to finish up this video. Classify the following reaction. I have phosphorus plus chlorine going to form PCl3. So now we will notice that this is not an acid-base neutralization because we do not have an acid or a base. Are we burning anything in the presence of oxygen? No, so this is not a combustion. Is this a precipitation? Well, no, because we do not have aqueous solutions going and forming a solid product. And this cannot be a decomposition because we're actually forming a unified product. So this is going to fall under a normal redox reaction. So this is a redox reaction by name, and it would fall under the combination subclass and family. Let's go ahead and look at this example. So now we are going to have H2SO4 plus MgOH2 going to form MgSO4 SO4, and water. So is this a reduction reaction? If this was a reduction oxidation, we would see a change in oxidation number, and we will not have that. Now, this is important here because B, for an acid base, we will notice that we have sulfuric acid. Plus, in the case of an acid-base neutralization, we are going to take an acid and a base to form a soluble salt that we see right here and water. So in this case, we are going to have an acid-base neutralization. So let's look at the other ones. This is not a combustion because we are not burning anything in the presence of oxygen. We would need to have an insoluble salt precipitate out and form a solid. And finally, for a decomposition, we would need to have something break down. Our correct answer for this example is going to be answer B. In this video, you saw many different reaction types that you would need to be able to identify by looking at them and their reaction characteristics. For the rest of this chapter, we are going to delve into many of these and look at them at a much better detail. Have a great day.